All right, well, thank you for your patience. And now we are starting our talk, My Journey into FM RDS, Radio Data System. Oona Räisänen. Please give her a warm round of applause.
Thank you. Yeah, sorry about my MacBook Pro. My name is Oona. I'm a signals hacker and electronics hobbyist. And I do this thing only for hobby. And let's see my slides here. Some of you may remember my blog or have read it. And you may have seen this one that I also made, the dial-up. That's the dial-up diagram. Well, this talk is not about that, but just to give you some context. Okay, so into the story. One night in 2007, I was listening to my radio, just an FM channel, and some music going on. And I was looking at the spectrum, of course, on my PC while doing that. And I noticed, I see the audio, that's normal, but then above the audio, at about 90 kilohertz, there's something weird going on. There's a persistent sinusoid tone, and something looking like sidebands on both sides of it. And I wanted to find out, what could it be? What could it be up there? Actually, I have some audio on my other computer. Just a minute. So this is just a radio channel playing, and I'm stripping the frequencies down to hear what it sounds like up there. Now at the moment it just sounds like a very piercing tone of 19 kilohertz, just a tone. And I'm not actually hearing just yet what's around it. But let's turn it down a bit further. Now this is one of those sidebands that you're seeing there. And I'm also now filtering out the music to make it clearer. It sounds very periodic, so it means it could be data of some kind. And it also brings up the memories of those modem sounds. So I started to investigate this matter a bit further. Now what I knew already that in the RDS signal there is the FM signal, there is the RDS data that is used to that is used to send to car radios the station name and the program currently running on it, and also some other information like alternate frequencies that this channel is broadcast on, CT, which is clock time, and something else, information about other programs on other frequencies, and the program type, radio text, traffic announcements, and something called TMC, or traffic message channel. So I thought, could this be it? So I downloaded the 200-page RDS standard, or RBDS as it's called in the United States, and started to do some analysis. I actually spent nights reading this, and many times I fell asleep reading it. It was if you suffer from insomnia, I suggest you read something like this. And what did I found? Well, it was very it was very well documented, the protocol. There was, for example, this diagram about an example receiver for RDS. There's all the parts out there. There's the FM signal is coming in, the audio is taken out, and we are mixing it with some frequencies to get out the RDS signal and all that stuff. So, well, using this information, I wrote a decoder in Perl. Everything was in Perl. And thank you. And I came up with this. It's showing a lot of the information going on the frequency. And what's special about this is that it's only decoded from the signal that you were hearing on the 90 kilohertz band. And it turned out that this is actually an error in the working of my radio, because I dropped it on the floor when I was moving, and it started behaving weirdly. And it was then when I got this weird signal on the 19 kilohertz band. And it turned out that the stereo decoder in my radio had somehow started, not filter anymore the stereo signal, which is near the RDS signal. So this is actually being decoded from the audio, from the line out of my radio. Nothing else was involved with this. But then, well, it's a bit noisy. It's near the 16-bit quantization noise limit of my sound card. So I was thinking of better ways to decode it with less noise. And I started to look at my radio, the schematics of my radio, and I found that there is actually a decoder circuit for RDS that it uses to display the data on the screen, just the station name and update its clock. And unlike in today's receivers, the RDS chip is actually on its own chip, and it's not a one-chip wonder receiver. So I found the 4 pins that I needed for data, clock signal, and ground, and just a quality bit that I am not actually using. And I did some ugly soldering work because I didn't want to remove the RF shielding from this chip to, well, hook some cords to the decoder chip. And then I used my sound card to sample that, because it so happens that the voltages that the sound card is using are very close to the logic voltages of just like general voltages of ICs in the 1 to 3.3 volt range. So I actually used a sound card to sample the logic coming out of there. And it's 1 kilobaud, so it's not even very fast. Oops, wrong computer. And this is what I was getting at first. Well, it looks like bits, kind of. Then, after some filtering and resoldering, this is what I got. Red is left channel in the sound card that I hooked up in the clock signal output, and green is what I hooked up in the data signal. And it's very clear. And the data can be decoded with no errors in this, from this. Afterwards, I also made a Raspberry Pi version of all this. So the Perl code is actually running on my Raspberry Pi and displaying it on a little LCD next to it. But then, okay, this is fun. I can actually see more than my radio is displaying there. I can see the radio text. I can see a numerical code for each station, so I can log these stations. And I only need to decode a number to know what I'm listening to. But there was something more on the frequency. I was getting an application, some application running there that I didn't recognize right away, but reading the standard, it became apparent that this TMC that is used in these car navigators to just send information about traffic jams and construction work and things like that. And of course, for the fun, I had to see what's going on there. Now it turns out that in Finland, the RDS signal is encrypted for reasons of commercial stuff. I mean, it's a business model. They encrypt the signal and they sell the encryption keys along with these navigator devices. And what they tell about the encryption in the standard, they actually tell everything about except the keys there. But one sentence especially caught my mind there. The encryption is only light, but was adjusted to be adequate to deter other than the most determined hacker. Yeah, and obviously for a hacker, this feels like a challenge. So I got to work. It was textually documented. There was no encryption diagrams or anything like that, but this is what I came up with. It's a pretty simple cipher. The location is a 16-bit reference, database reference to a database of locations that can be obtained from the manufacturer of the navigators. And the key is 16 bits. Key space is 16 bits. And different parts of the key are used to, like, parameters for the different operations in this cipher. And it's an easy enough cipher to be used on paper also. So when cryptanalyzing it, I made some tests on paper. So how do I begin? I can't just brute force it, just knowing nothing about the transmission. So I made some assumptions. The bandwidth is very low. It's several hundred baud. So there must be some kind of filtering with these locations. I was thinking it could be that they are sending only the locations, only the announcements that are near the transmitter, like 100-mile range or something. So I looked at the location database that I, by the way, obtained by telling the manufacturer that I am an engineer and I want to do some tests and maybe some development of RDS TMC software. And now I have the database. So I started mapping, actually listening to the announcements. I took one announcement and I figured, well, one announcement is on for several days in a row, actually several weeks, because when there's a roadworks on, it could last for months or weeks or something. So one day I get the announcement and I get the key ID, which they are sending in clear text. Well, that's how they signal what key is in use today, because it's a changing key scheme, and there's a different key for every day. And then they send the encrypted location. So I listened for several weeks in a row, documenting the encryption key ID and the location. And then I just brute forced through the whole vast 16-bit key space to find all the keys that decrypt into locations that are near the transmitter. And eventually, I came up with all the keys. And here they are, because I wouldn't want to get in any more trouble with this. Well, yeah, I ended up finding all the keys. And here is a prototype receiver that I wrote. It's receiving the messages and showing me a little map of the announcement. So then I published this in a blog, and I got an interesting reply from someone who is involved in developing this. Sad request, but can you take this offline? It is kind of our service you hacked. Yeah. Okay, I had promised in the beginning of my blog post that if any involved party requests to take this offline, I will take it offline. But of course there are, well, my definitions of an involved party are quite strict. And I replied by requesting just the same message, but signed with their cryptographic signature. And preferably, I could fetch their public key from under their company domain. And they never replied, so the blog post is still on. Yeah, and actually, while this conversation was going on, it was, of course, being copied all around the world and in cryptome also. So there was no point in replying anymore. So yeah, this was the first part of my adventure into RDS subcarriers. Then I heard a rumor when presenting about this that the bus stop displays in Helsinki also received their data about the next buses on RDS, on the RDS signal. So I started to look a bit more on the applications, but there was nothing in the application list about bus stops or anything else on TMC. For reference, these are the displays I'm talking about. So they are displaying bus number and the minutes and where it's going, and it's updating live. And these are battery operated, and they are not connected to anything by wire. So there must be some kind of a radio protocol, but this was a nice clue. So I started Googling about this. There was not very much information about it, except for the Finnish Communication Authority's internal magazine. They were telling about all kinds of, sorry about my French, I'm in Finnish, of course. But they were telling about all kinds of everyday radio signals, and they confirmed my guess that it's being transmitted on the FM radio. And they even told the channel, but that's all they told. They were just telling it's been transmitted on wirely 1 frequencies. No protocol, nothing about RDS. So I fired up my other radio, which can do a larger spectrum, which is of course the Realtek RTL SDR packaged in an aluminium tin here. So I demodulated the wirely 1 station signal on a bigger bandwidth. And here's what I saw. On the left, there's the audio. And there's the obnoxious tone you just heard. Here we have a stereo separation signal that tells the relation of the left channel to the right channel. Here's RDS, where it actually should be, but for some reason it was aliased to around the pilot zone in my older radio. And this fourth harmonic of the pilot zone contains obviously some data on a very wide bandwidth compared to the RDS. What could it be, and how could I ever find out? Well, it's centered around 76 kilohertz on the demodulated signal, the composite signal. So I started by Googling for 76 kilohertz, and I found something called dark or data radio channel. It's not to be confused with RDS, which is radio data system, of course. And these are very imaginative names. And I found out it's a very much more complex modulation scheme. It uses QPSK, which is a 4-phase modulation scheme. And well, I'm not an engineer, not a DSP specialist. I'm a DSP hacker, but I don't know much about demodulating QPSK. So I decided to treat it as an FSK signal because that is possible with QPSK. You can, it's how should I say, suboptimal, but it works. I can get the data out. So the upper part is the dark signal filtered. Here's the dark signal using two bandpass filters that are on 76+4 and 76-4 and superimposed in red and blue, so like an FSK. And here's just blue minus red, or the other way around, which is actually binary data. And yeah, I had to treat the error correction and error detection. It was very complicated, and I had to write a general CRC subroutine in Perl because I had to deal with such large numbers that I couldn't use just integers. I had to actually use string magic. So I'm actually concatenating strings of ones and zeros and using this kind of general CRC routine for calculating the error correction and detection. So this is dark, and I am actually getting packets out, but I had no idea what the packets mean. So I started looking for any human readable data out of there, because there is no documentation about this. And for example, this was one type of packet that I found, ruskea suo bruna kärr, that means something for Finn. It's a place in Helsinki where the bus 23N happens to go. So I figured this could be a packet telling something about, just generally about buses. And actually I went so far as to label all the fields in the end because I collect so many of them. And I found out that the system is sending one of these packets to every display once a day. So it's updating the information about all possible buses that are passing this bus stop today. And yeah, it's using such low bandwidth that updating all the displays takes one day. Then I found another type of package with no actual strings, but I found definite references to the above packet. And I found this is the packet used to update the minutes information in these displays. It's being sent very fast, 3 times per minute per every display. And it contains minutes for 6. I can count 8 buses per packet, and information about whether they are actually GPS located or it's this guess based on timetables. And I used all this information. I had a functional goal to build my own display because the tram stop is 200 meters from my house, and I can't. And I want to know when the tram is actually coming, because this information is actually the GPS located information. So this is what I built. Yeah, it's just a basic HD 77480 display controlled by a Raspberry Pi, decoding the signal from the RTL SDR. And for some reason this, I blogged about it, and it became very popular in Finland, in Helsinki especially. And there was a news article about it, and And someone, a representative of the bus company, was telling that, okay, she can decode the signal, but transmitting will be difficult, and yeah, I haven't actually done it yet, but he was saying that it's difficult because you have to shout louder than anyone else on the frequency, and even then it becomes mangled because it becomes a mix of those two signals. I don't think he really knew what he was talking about, because there's something called the FM capture effect, that if you send stronger than another FM transmission on the same frequency, only the stronger becomes captured, and the weaker becomes actually attenuated. And that's a very useful phenomenon. Right now, I'm actually in the process of making my own display updater for possibly for showing all kinds of funny stuff on the displays. And someone at the bus company actually donated one of those displays for me after this, so I have something to test it on, because obviously I'm not going to transmit any high power signals with this ever. Yeah, but right now I'm building it. The only problem that I'm having right now is that my sound card that I'm using to generate the signal, fully digitally of course, is too slow, and the dark signal is 76 kilohertz, so I need at least 162 kilohertz sound card, I mean DAC, to create my analog signal. I only have a 96 kilohertz sound card right now, so I can only generate the stereo signal. But perhaps in the future, that will be my next project. Thank you.
Well, thank you very much, Ona. I think we are all impressed with hacking a radio. I've never thought about this opportunity. Now we have time for questions from the room. If you want to ask questions, could you please line up at the microphones right here? And in the meantime, let me ask our signal angel. He has a question from the internet. Could you tell us, please?
Yeah, so the internet wants to know if there is any open hardware radio receiver you can recommend for tinkering at home.
Yeah, the RTL SDR is a very good piece of hardware to start with. I think I have one of those with me right now. I mean the one that I showed with the Hello Kitty tin around it. I'm using the tin to attenuate any local interference. But it's just a DVB, digital TV stick. Some wise guy on the internet found to be possible to hack and tune to any frequency from 30 to 1700 megahertz. And it's very useful. Doesn't go higher than that, doesn't go lower than that, but it's a good start.
Okay, questions from the room. Can you start, please?
Hey, hello.
Hello.
I have just a bit of input on your transmitter thing. There is a project that uses the Raspberry Pi DMA controller to where you can use to send signals at about 140 megahertz on the GPIO pin. So maybe that could be used.
Ah, thanks for the tip. Yeah, that would be very useful. I've been thinking about the GPIO, but it's unfiltered, of course. And
the raw DMA controller output just gets dumped onto one of the GPIO pins. Mm-hmm. And as far as I know, it's good enough to transmit FM stereo audio.
Okay, yeah. Well, it would be worthwhile testing with RDS first, maybe. Thank you for the tip. Yeah, very useful.
So maybe we can buy them at the next Congress then, right?
Could be. Mm-hmm.
Okay, go ahead, please.
Hi, thanks for the interesting talk. I have two questions, in fact. you said that you can decode QPSK as FSK.
Yeah.
By a simple trick. How much less quality do you get? 3 dB, 6 dB, what is it?
I'm not sure about the details, but well, it just crossed my mind that you can do it. Okay. It's actually MSK, but it's a sort of a QPSK signal. Okay. So it's a minimum shift keying. And that's essentially being generated in the transmitter as FSK, but as a special form of FSK.
Okay, thanks.
So that's why it can be decoded as FSK also.
And the brief second question, in the picture where you took up the digital signal from your radio, it was a Sangean ATS 909, or which one? The radio used?
The chip. Or the
the radio. I've got one of those, and I was wondering if I could pick up the signals in there as well.
This one?
Yeah.
This Sangean ATS 909.
That's what I said. Many thanks.
Yeah. I just modified it a bit, and you can take a look if you want.
Okay. Any other question from the internet? How about our signal angel has nothing? Then let's go ahead right here, please.
Thank you. Have you considered what are going to be beyond transmitting this signal? What are going to be your next challenges you're taking up? Are you going to look at other wireless services that are around there in terms of utilities? Because traditionally there are many.
There are many, yeah. It's a very interesting world. And I'm actually, I'm listening to several signals at the moment at my home right now. And well,
mind telling us a little glimpse?
Well, there's the local taxi company that is using the frequency range from 40 to 70 megahertz to send information about next clients and also locating all their cabs. And I'm trying to decode what it's all about, and if I could perhaps make a map of all their cars. Of course, there's also Tetra. Not many people know that Tetra is not encrypted. It's usually encrypted, but not always. And many applications in Tetra are in the clear text. And you can listen to it if you really want to.
Which sort of teases me now to ask a question. Out of curiosity also for me, what's the legal situation for you in Finland when it comes to decoding such transmissions? When they are not encrypted?
You have the right to remain silent here.
No, you don't have to answer, but...
Well, I believe it's legal to decode them. I don't care if it's not, but... yeah, of course, actually making an FM transmitter would be illegal if it's high enough power.
Yeah, Ficora might object to that.
Yeah.
Okay, over there, let's go, please.
Thanks. Could you maybe elaborate a bit about the bus stop packet contents? Apparently, they're not encrypted. Is there any signature to verify that it's a legit packet?
No, they are not using any encryption or signature overhead because it's such a low bandwidth channel. So you can spoof it. It's, I guess it should be trivial. Actually, there are some types of packets that I don't know the meaning of, but they are non-changing, so they obviously can't be any signatures or anything like that.
Okay, go ahead, please.
Okay. I wanted to add some information on the situation in Germany. We have two types of radio stations. The public radio station broadcast RDS data unencrypted, so you, if you get the RDS data, you can just get the raw location codes, and the TMC messages are usually sent by private radio stations. The fun thing is that you get both. You get unencrypted location codes and encrypted location codes. So if you listen to two radio stations in the same area, you can actually cross-correlate these and try to figure out the key. And the other thing I wanted to say, if somebody is just interested in RDS data, there are cheap, relatively cheap USB sticks which do all the decoding for you.
Yeah, FM radio sticks.
Yeah,
right. That's true.
Okay, thank you. Go ahead, please.
Is there any book you can recommend in getting started for processing of digital radio transmissions?
Well, I've read a few chapters of the, I don't know the name actually, but dspguide.com or something, Engineer's Guide to DSP, something like that. It's a blue book, that's all I know. But that's a good one, and it's freely available online. Just should probably Google it.
All right, thank you.
Thank you.
Okay, any more questions? And from the internet? Nothing right there. Okay, well, Ona, thank you very much. It was a very interesting talk, and we look forward to having you again next year with more signals.